Hello, we are in between, this is an in-between video, just by the way, between part 6 and 7, I think, of building the new query UI. Since last week I discovered, it wasn't necessarily a bug, but a big problem with my current query engine implementation, and so I wanted to get that fixed before I continued making the UI builders, so I'm doing kind of just this little video, mostly just to talk about the stuff that I changed and to fix, and then I'm gonna make a separate one for the query builder, in case you just want to watch that or something. But um, I'll try to keep it brief for this one. I might talk about a little bit of code and stuff, but it shouldn't be super long because I'm not gonna be doing any actual coding in it. um, but here, if you want to read about, I don't know, if you want to read about the problem, I wrote this short kind of tech note on it. It's here just in the repository timeline, so you can look at that. Um, but basically, the problem that I noticed with querying, specifically for subtags, is that you could have, like, say we have these two files A and B, and they would have these two different sets of tags, right? So on file A, you have this tag A that's subtagged with B that's subtagged with C, and then on file B, you have an A that's subtagged with B, and then you have a D that's subtagged with B that's subtagged with C. So then the particular issue that was coming up was if you ran a query that was searching for this A sub B sub C, then both of these files would appear in that query when only file A should be appearing in that query. And that's because before, in the implementation I was using before, when you do a subquery search or a subtag search, basically you have like these different kind of layers. So you have like this AB layer, and then you have this BC layer to the query. And the query engine, what it was doing before is it would run a query on AB and get all files that match that AB criteria, and then it would run a completely separate query that would do BC and get a file set for that, and then it would basically just intersect those file sets together and then kind of just assume that that file set, that intersected file set, would be the same as what this query was intended to search for. So that's why we got both of those results, because they both have an AB, so they would both match on that first term, and then they both have a BC, so they're technically not part of the same set, but that implementation before was flawed, so they would both get returned for that. So that was something that I had considered when I was writing the original implementation, and then decided that it was probably I think I made a couple of kind of erroneous assumptions with that, in that I maybe just didn't understand the problem or scope of the problem enough to be able to say that the implementation I was writing was flawed, or I decided that maybe it wasn't that big of a deal and that I could just ignore it. But I do remember thinking at the time that I was writing it that doing that approach of AB and then the separate BC query was a pretty naive approach. So now with this last week of me working on this, it was basically just me fixing technical debt from when I originally wrote that engine to actually do it properly. So I think what I've done now is I've settled on a more accurate approach to it. It's not necessarily more performant, which we'll talk about. There are kind of a number of I don't know, considerations I had to make that was making this new query engine quite a bit more complicated than the previous one. But essentially, right, so we talked about what this implementation was before. What the actual proper implementation needs to be is that you run this AB query, and then you build up a set of tags with that, right? Tags and not files. So you build up a set of tags that match this criteria. So you start, and actually, hold on. Let me start from the beginning with this query, right? So the first step, what you want to do is you want to find all files tagged with A, right? So that'll probably return like a ton of files, and all those files will have some A on them that may or may not have any subtags at all. And then what you want to do is then run a query of files that have an A that is subtagged by B, and then that'll give you a different set of tags. And then what you do is you take that original set of tags from A and then this new set of tags from AB, and you intersect them together, where the subtag of ID column from this AB query is matched to the tag ID column of this A query. Excuse me one moment. Sorry. Have a little bit of beer. So I'm trying to think if I should pull up the schema or something. But basically, okay. So the way that the tags work, right, is that there's a tag table that consists of 4 different columns, and that table has a ID, right, which is just a primary key for that tag. It has the file ID, where the tag points to the file that it tags, obviously, and then the descriptor ID, which is that descriptor that is applied to that file, so that's like the actual text, and then the subtag of ID, which is actually a foreign key to a tag ID. I don't know, maybe foreign key is not the right word for that, but the point is that this tag table has defines recursive relationships like that. So it may not necessarily be clear what I said before when I meant that these AB tags would be joined with that subtag of ID to the tag ID. So sorry about that if I didn't make myself clear. I'm probably kind of rambling a little bit as well. And then let me think. So after you find that tag intersection between this AB and then the A, you then go to the next level and you run that BC query, and then you do the same thing where you intersect those AB IDs with the BC subtag of IDs. And then that'll return to you a final tag set, and then from those tag IDs you just go and retrieve their file IDs so that you can get the actual files back. So excuse me. So that's the new approach, is doing it that way. So you basically just build up. You start with an initial set of tags, and then successively join it with the results of another tag query, right? So my first thought doing this was to actually just write pretty much a full-on SQL compiler, right? That would take a tagger QL query and then just compile it to SQL. So like this is that same ABC query in its compiled form, how I would see it. So you start with A here, so like it's all the way down here. This is your initial case, and then you successively join it to these B and C kind of like, you know, grouped subqueries. In those joins, like let me think here. Those joins are here, right? So subtag of ID is joined to the super tags ID. And then by the time you're done writing those queries, then you just join it to the file table so that you can get the actual file objects out. So that was my first thought, was to just compile the SQL, right? So I figured that I could have done that from the very beginning with this project, is just compile the query language to SQL, because it's not doing really anything super complicated under the hood. Like, these are all pretty generic subqueries here. Like you can see, they're all the exact same thing except for whatever the parameter is in them. So it's like not super complicated. But I really wanted to avoid actually doing like actually compiling, right? Because these queries can get quite long, and I just didn't want to do that. You know. I would prefer not to like actually concatenate SQL queries, and I would rather just use the SQL library as it was intended to, where you just have simple queries and you bind a static number of parameters to them. Like, it's not necessarily a good thing to need to be able to bind a dynamic number of parameters to your SQL query. You can get into trouble pretty fast with that. So I was considering doing this, and I wrote one implementation that was basically like this early in the week, and I guess I wrote my queries incorrectly or something like that, because it didn't quite work the way that I wanted it to, and it was really quite error prone, because, I mean, obviously, when you're writing SQL um, in Haskell, like, you don't have a, let me find this module real quick. You don't have like a SQL language server or linter or anything like that, right? So it's really easy to just make typos in your SQL queries like this. Like there's no, there's no extra information. There's no sort of like IDE info or like spell check or IntelliSense or anything like that. So that's one thing that makes it kind of difficult. Just like concatenating a bunch of queries is it's really easy to make small mistakes like that. It gets really complicated too when you try to just concatenate parts together instead of just writing a full query out, because then your queries start to look like, excuse me, your queries start to look like this, where you have like some stuff that's really pretty comprehensible, and then, excuse me, and then you have these Haskell functions mixed in, and you have to have these variable names and stuff like that, so it can get quite confusing pretty quick. So this is the most complicated piece of query concatenation I have in this entire library. I don't actually concatenate a query anywhere else. This is the only place in the whole library that I actually just build a query out of separate parts. Because I didn't really want to do that at all. So that was why I decided not to do this, but rather to kind of just emulate that, just using function arguments. And specifically for this, I used a reader monad. And probably not the best use case for a reader monad, because I could have just done the same thing just with having an extra parameter to my function. But I don't know, reader monad helps to keep things kind of nice and simple. And a reader monad, I suppose, just for the sake of mentioning what it is a monad that has some type, and in this case it's this query environment type, which just has a hash set of tags, and then my database connection for convenience. It has this environment where the environment is immutable, so you can only read from it, but you can perform calculations with the environment and stuff like that. So that's pretty much all you really need to know about a reader monad. The way that I typically use reader monads is just a way to like encode implicit function parameters in every function, right? So this function here takes two terms and returns a query reader, but because it's in a reader monad, it actually has pretty much an implicit query environment as a function argument. You just don't see it and you don't have to think about it, but if we needed to access those things, then we can use either that hash set or the connection in it, right? Like if I wanted to access those things, then you can just do like you can just do that, and then it'll retrieve that tag set for you out of that reader. So that's pretty much how you use readers, is you just like you can kind of hide information in them or keep immutable information in them. Right. So, and then with this query reader, what I did is I was just emulating these joins specifically. So you build up this tag set in this reader monad, and then at certain points in the query, you would intersect two tag sets together, and you would use I wrote a function for it somewhere. You would use this function, right? Which all it does is it basically just does the SQL join. But it has to do some extra stuff like retrieving the subtag IDs and tag IDs and stuff like that. But it just merges these two hash sets together on that key, just like that SQL statement. So I'll show you the actual kind of the engine part. So these are all just ways to construct queries. I was trying to do it a little bit more dynamically because my previous implementation I wrote out all these queries by hand and they were really quite long. And in this case especially, like most of the query parts, like we saw in that one example, are all the same. So you don't have to handwrite them, right? You can just make a generic one with this parameter, like the super in here, and then just add them together. So, and I don't mind doing that for these because they don't have a dynamic number of arguments. I know in this function here, there's only this clause and this clause, and they both have named arguments, and I know exactly what the arguments are, and that there are exactly 2 of them. So I don't have a problem with that because it's not a dynamic number. It's always 2, and it's always an argument called super and always an argument called sub, so I didn't have an issue doing that. But basically, these are all just functions that will produce this query, and then you just run this query with your connection, and it'll return a tag set, hashtag, or hash set of tags. So then, in the actual query engine, most of these functions are from the previous implementation. All of these are fine. The only real problem with the previous query engine was this query complex term function. That was where all the problems were. So I rewrote that completely to use this query reader. So I apologize for the dark mode and light mode clash, I guess, of my browser, but so here all this function is doing is it's a recursive function, but it has this initial case here that gets called in the actual query engine, and then this initial case will call the lower cases. And the reason for this is because, like I said before, even though you're querying on relations, you have to start with the first tag. So this will just query for that first tag and get an initial tag set, and then I said before that the reader monad is immutable, but what you can do with it is do kind of local mutations, right? So you do this function local, and then you can modify the environment to run one computation with that modified environment. So it's really useful to do recursive functions because you can just modify the environment only for those lower recursion calls, right? And you don't have to worry about any of your mutated data kind of leaking back up to the top like you would if you were using a state monad. If I was using a state monad and I changed state in the monad down here, that state would be changed up here, and I don't want that to happen, right? I only want changes to propagate downwards and not be available to the whole function. So that was why I used a reader monad specifically. Right, so you query here for this first tag, and you build an initial tag set. You set that tag set to the environment, and then run a local computation with the body of this function. So this is a depth first tree traversal, I'm pretty sure. And basically what it does is it will start from this leftmost relationship and then query downwards until it reaches the very terminal case, which I'll kind of get to that. And then when it reaches that terminal case, it'll return a file set. And then after it returns that file set, it'll go to this next relation. Here, actually, that's not quite a good query for that. So here, I'll show you this one. So here's a good one that would illustrate this. So you have some A sub B sub C, and then A sub D, and then sub E sub F, like that. So what this function does is it'll first go to AB, and then it'll go to BC, and then it terminates depth-wise after BC, so it'll return a file set after running that query. Excuse me. After it returns that file set, it'll then go to this A sub D relationship, this one, and then it'll go depth-wise there, so A sub D, and then D sub E, and then E sub F, and then it terminates in the depth case on E sub F. And then now that'll return a file set, and then now since you're at the furthest kind of right point in that query, it'll take all the subsequent file sets that have been built up, and it'll intersect them together, which is what I want it to do. It's not like last time where it's like a miss feature or a miss implementation. That's what I had in mind from the beginning when you have these kind of like parallel subterm queries going on. Right, because this is asking for a file that has A sub B sub C and a file that has A sub D sub E sub F. So you have to query on file sets there, because those are two different tags. Like those would never intersect with each other if you were trying to just do tag intersections. So those intersect on the file set. So this function just does that, right? So here's our first case. This is the terminal case. So something is a bottom when it's in this subterm, but it has no subtag after it. So like this C would be a bottom. So like this bottom terminal is just that term C. And then these parallel subterms would be pretty much like these. Though for that case of C, there are no parallel subterms, right? Because otherwise it would have to be like that. So if we had something like that, then this Z would be a parallel subterm. And like I said before, right, so we're at this terminal set, we get that tag set, we then join it to our environments tag set, so that initial environment that we set up, or whatever environment we currently have, right, and we join those together, doing that kind of SQL type join. And then what we do is, depending on if we have any of these parallel subterms left, then we'll do some queries on those to intersect their file sets together. Otherwise, if there are no parallel subterms, you just return this file set, right? Because if you just map over the list regardless of whether or not it's empty, then it'll return an empty file set. And if you intersect an empty set with any set, you're going to get an empty set. So we don't want to do that. So that's why we have to have this case here for that. Just for that reason. But this is our terminal case. So this is the depth part. So this this is the actual terminal case for this function. We have these two kind of pseudo terminal cases here, where if you ever just have a bottom, like if you're ever just querying for this C, then it'll return an empty file set, because both of these cases are actually unreachable. These cases will ideally never be called. We just have them there just for the sake of having a complete function, but neither of these will ever be called, because the case terminates one level above that, right? The case terminates on this BC query and not on the C query, just in case you were wondering. And then here's our non-terminal case. So this is like an AB query, where we have some file set we need to intersect, but we also have some deeper tags that we still need to query. And so this is finding a tag set and then joining that with the environments tag set, and then it's doing another recursive local computation with the lower tag set, right? So it queries for AB, it gets a tag set, intersects that with all tags A, and then does a local computation for that next query BC. So that's in a nutshell what that function is doing. This is after like 3 or 4 rewrites, so it took I don't know, quite a lot of thought to do this, even though it's very similar to my tagging function, which is here. It's very similar to this function. Both of these use reader monads. They operate in pretty much the same way, honestly. And I didn't really get the idea to write them like that until I had already kind of re-implemented this whole engine like 2 or 3 times. And I was like, well, we already have the tag reader that's doing something really similar. Like, it's already querying for tags as it goes. And like before, when I was messing around with the SQL queries, like I'm joining on tags. So it's really kind of the perfect use case for this. So anyways, I don't know if I was making any amount of sense at all, or if this was interesting at all, explaining how this works. But this basically, this function and this module consumed probably between like 12 to 15 hours of my life this week, I think, as I was working on that. Oh, really over like 3 or 4 days probably. So now that I've explained that, I'll probably just post it just like as an extra to my channel, I suppose, and continue on, I think, with part 7 of the Query Builder UI video or something like that next time. So yeah, thanks for watching. I'll see you maybe in like a day or two when I do the next one.